Did you know that everything you have ever seen, everything you have ever touched, every mountain and ocean and star and galaxy and atom in the entire observable universe, all of it was once compressed into a space so unimaginably small that it makes a single grain of sand look like an entire solar system by comparison? And did you know that in a single moment, in less than a fraction of a second, all of that matter and energy exploded outward in an event so violent and so total that the shockwaves from it are still echoing through the universe today, more than 13 billion years later, and we can still detect them with our instruments? This is the story of the Big Bang, the beginning of everything, the moment before which there was no time, no space, no matter, no energy. It is the story of what NASA and the world's leading scientists have recently revealed about that moment. Revelations that are shaking the foundations of cosmology, challenging some of our most deeply held assumptions about how the universe began, and opening doors to possibilities so strange and so profound that they force us to completely rethink our place in the cosmos. Because here is the truth that most people do not realize. The Big Bang Theory, despite being our most successful model, still has gaps, still has mysteries. It still has questions at its very heart that nobody has been able to answer. Stay with me because this goes deeper than you think, and some of the most recent data coming from NASA's most powerful space telescopes is not just filling in those gaps. In some cases, it is making them bigger. It is revealing anomalies and contradictions that suggest our current understanding of the Big Bang, as good as it is, may be fundamentally incomplete. This is not a story about science being wrong. It is a story about science doing exactly what it is supposed to do, pushing further, looking deeper, asking harder questions, and refusing to stop at comfortable answers when the data says there is more to discover. So let us begin at the very beginning. Let us go back as far as it is possible to go. Let us try to understand what the Big Bang actually was, what we know with confidence, and what we do not know. What are the latest discoveries telling us about the true nature of the moment that created everything? Stay with me till the end to see the full picture. The further we look, the more we realize that the universe is not just stranger than we imagine, it is stranger than we can imagine. Some scientists are even beginning to wonder if the Big Bang was a beginning at all, or simply a transition from something else entirely. NASA's upcoming missions are designed to peer through the cosmic fog of the early universe, looking for the first stars that ever flickered into existence. This is the greatest detective story ever told. If you want to stay updated on these cosmic discoveries, make sure to like and subscribe. I read every single comment, so tell me your theories below. If you're ready for more, comment the keyword space to show you're committed. Until next time, stay curious. This is your host signing off. Allah Hafiz. To understand the Big Bang, you first need to let go of a very common and very understandable misconception. When most people hear the words Big Bang, they picture an explosion. They imagine a point in space surrounded by emptiness, and then a tremendous blast that sends matter flying outward. This image is natural, it is intuitive, and it is wrong. The Big Bang was not an explosion in space, it was an explosion of space. There is a crucial difference. Before the Big Bang, there was no space. There was no empty void waiting to be filled. There was a true and total absence of anything at all. What the Big Bang describes is the moment at which space itself came into existence and began to expand. Every point was once compressed into an infinitely small singularity. And then that singularity began to expand. Not into anything. It simply expanded, creating space as it went. There was no center, there was no edge. This is one of the most difficult concepts in all of modern physics to wrap your mind around. And it is also one of the most important. The universe did not begin in a specific place. It began everywhere at once, and it has been expanding ever since by the very fabric of space itself stretching outward. If you imagine drawing dots on the surface of a balloon and then blowing it up, the dots represent galaxies and the surface represents space itself. As it inflates, every dot moves away from every other dot. No dot is at the center. No dot is at the edge. The expansion is happening in the surface itself. Stay with me because this leads us to the evidence. This analogy was first developed by Georges Lemaitre in 1927, and it was confirmed observationally by Edwin Hubble in 1929. Hubble discovered that distant galaxies are moving away from us at speeds proportional to their distance. The further away a galaxy is, the faster it appears to be receding. This observation gave scientists the confidence to extrapolate backward in time. If the universe is expanding now, then in the past it must have been smaller. And further in the past, smaller still. Eventually, you arrive at a moment when everything was compressed into an unimaginably small, hot, and dense state. A state where the laws of physics break down, a moment we call the singularity, and the transition from that singularity to our universe is the Big Bang. Understanding this shift in perspective is the key to unlocking the rest of the cosmic story. Like, subscribe, and comment space to keep exploring with me. Allah Hafiz. The idea of inflation is both simple and mind-bending. Guth proposed that in the very earliest moments after the Big Bang, the universe underwent rapid expansion. An expansion so fast and so violent that the universe grew by a factor of at least 10 to the power of 26. Something the size of a proton expanded to the size of the observable universe. This sounds insane, like science fiction, but inflation solves all three problems elegantly and simultaneously. First, the horizon problem. Regions that today appear beyond each other's horizons were, before inflation, so close together that they had plenty of time to reach the same temperature. The flatness problem is solved because inflation stretches the geometry of space so dramatically that any initial curvature becomes negligible. No matter how curved it was, inflation ironed it out, just as the surface of a giant sphere looks flat to an ant standing on it. The monopole problem is solved because inflation dilutes them so dramatically that the chance of observing one becomes essentially zero. They effectively disappeared. Inflation was a theoretical triumph. Over decades, it has been refined into a sophisticated framework that makes specific, testable predictions. Predictions that have been confirmed by observation to a remarkable degree. But here is where the story takes a fascinating and unsettling turn. While the broad predictions were confirmed, the detailed fingerprints inflation should have left, particularly on the cosmic microwave background, have not all matched. The discrepancies that have emerged are now at the center of some of the most intense and exciting scientific debates in modern cosmology. We're standing on the edge of a new understanding. Like and subscribe to see where the data leads. Comment space to show your commitment. Allah Hafiz. Now here is where things get genuinely interesting. Because the Big Bang Theory, despite its enormous success in explaining the large-scale structure of the universe, has always had several serious problems. Problems that physicists have known about for decades and have worked hard to solve. And understanding these problems is essential to understanding why the recent revelations from NASA and other observatories are so significant. The first major problem is called the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of heat left over from the early universe that fills the entire sky, we find that it is extraordinarily uniform. The temperature of the cosmic microwave background is almost exactly the same in every direction we look. The variation from one part of the sky to another is less than 1 part in 100,000. This uniformity is deeply puzzling. Here is why. The regions of the sky that we observe on opposite sides are so far apart that they could never have been in contact with each other. They are beyond each other's cosmic horizons. How did two regions that have never been in contact manage to reach the exact same temperature? It is as if you had two rooms in separate buildings with no connection, yet both were exactly the same temperature. You would want to know why, and in the case of the cosmic microwave background, standard Big Bang theory simply cannot explain it. The second major problem is called the flatness problem. The geometry of the universe, whether it is curved like a sphere, a saddle, or perfectly flat, depends on the total energy density. Observations tell us that the universe is extraordinarily close to flat, so close that the energy density today appears to be within less than 1% of the critical value. This is strange because in the standard Big Bang model, flatness is an unstable configuration. A universe that starts out even slightly curved will become more and more curved as it evolves. For the universe to be as close to flat as it is today, it must have been almost unimaginably close to the critical density in its earliest moments. The odds are so small that it is deeply unsatisfying as an explanation. The third major problem is the monopole problem. Magnetic monopoles are particles with only one magnetic pole, either north or south, but not both. Every magnet we have ever observed has both. But the physics of the extreme early universe says that monopoles should exist and should have been created in abundance. And yet we have never observed a single one. Where did all the monopoles go? All three of these problems pointed to a gap in the standard Big Bang theory, a gap that needed to be filled with something. And in 1980, a physicist named Alan Guth proposed what became one of the most revolutionary and far-reaching ideas in the entire history of cosmology. He proposed cosmic inflation. Stay with me because next we see how this changed everything, like subscribe and comment space, Allah Hafiz. The cosmic microwave background is the single most important piece of evidence we have about the early universe. It is the oldest light in the universe. Emitted 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form, making the cosmos transparent to light for the first time. Today, that ancient light has been stretched by the expansion of the universe to microwave wavelengths. It carries within it the seeds of everything we see today. NASA has invested enormous resources in mapping this light. The COBE satellite in the 90s first confirmed that the predicted temperature variations existed. UMAP followed in the 2000s with much greater detail. Then came the Planck satellite, producing the most detailed CMB map ever made, released in 2013. The Planck data was a triumph. It confirmed inflation's predictions with extraordinary precision. Cosmologists celebrated. The model appeared in very good shape. But hidden in the Planck data were anomalies, subtle departures, features that should not be there if our understanding of the Big Bang is completely correct. One of the most intriguing is called the cold spot. In the direction of Eridanus, this region is significantly colder than the surrounding sky. Some think it was caused by a supervoid. Others propose the unthinkable, the possibility that it's evidence of a collision with another universe in a multiverse. Then, there is the hemispherical power asymmetry. The standard model predicts the CMB should be statistically the same in all directions, but one side is different. There is also the so-called axis of evil. The largest patterns in the CMB appear aligned with our solar system in a way that has less than a 1% chance of being random. If the universe is truly the same in all directions, this alignment should not exist, and yet it does. And nobody has a satisfying explanation for it. The hunt for the truth continues. If you're ready to see what's next, like, subscribe, and comment space to show you're committed. Allah Hafiz. The anomalies in the CMB are interesting, but they pale compared to what has been revealed by the most powerful space telescope ever launched, the James Webb. Launched in late 2021, Webb was designed to peer further back in time than any previous instrument, seeing the light from galaxies over 13 billion years old. And what Webb found has stunned the community. It is finding massive, surprising, mature-looking galaxies where, according to our models, there should only be small, irregular clusters. These are the universe breakers. They appear to have formed extraordinarily quickly, challenging our most deeply held assumptions about how the cosmos evolved. Standard models predict the first galaxies should be small, but Webb is finding giants at epochs when the universe was only a few 100 million years old. Perhaps dark matter behaves differently than we assumed, or perhaps our measurements of the fundamental parameters of the universe are fundamentally incomplete. This brings us to the most pressing crisis in modern cosmology. It is called the Hubble tension, and it is keeping scientists awake at night. There are two ways to measure the expansion rate of the universe. One is directly in the nearby universe, using what astronomers call the cosmic distance ladder. The second is to infer the rate from the early universe, using detailed patterns in the cosmic microwave background. Both methods are incredibly sophisticated, and they give different answers. The early universe says 67, the distance ladder says 73. The gap between them is statistically enormous. Webb has been used to independently verify these measurements, and frustratingly, it is confirming the higher value. The tension is real, and it's not going away. Proposals like early dark energy suggest new physics in the early universe altered the results, but none of these theories solve every problem at once. We are bumping up against the edges of our understanding. The resolution will almost certainly transform our knowledge of the cosmos. Stay with me for the next breakthrough. The story of the beginning is still being written. Like, subscribe, and comment space to show you're committed to the journey. Allah Hafiz. But the revelations do not stop there. There is another set of discoveries adding yet another layer of complexity to the story of the Big Bang. In 1998, astronomers expected the universe's expansion to be slowing down due to gravity. What they found instead was shocking. The expansion is not slowing down, it is speeding up. The universe is accelerating, driven by a mysterious force we now call dark energy. Dark energy makes up 68% of the universe. Combined with dark matter, everything we have ever studied, every star and planet, represents only 5% of what's out there. The other 95% is invisible, unknown, and deeply mysterious. We know it exists because we can see its effects, but we cannot explain it. The most natural candidate is the energy of the quantum vacuum. But when physicists calculate its value, the math goes horribly wrong. The theory is 10 to the power of 120 times larger than what we observe. It's the largest discrepancy between theory and observation in the history of science. New 2024 data suggests dark energy might not be constant. If its strength changes over time, it rules out our simplest theories and points to new physics. Our standard model is enormously successful at predicting the cosmic web, yet it is straining at its seams from these unresolved tensions. We are standing at a frontier. Our picture of the Big Bang is incomplete, and this incompleteness is pointing us toward new physics we do not yet understand. Some believe the resolution lies in the multiverse. The process of inflation may never stop, continuously creating new universes beyond our own. If this is correct, our Big Bang was not unique. We might even find evidence of ancient collisions with other universes hidden in the patterns of the CMB. The search is on, and our tools are getting better every year. Thank you for journeying through the beginning of everything with me. Like and subscribe to stay on the edge of discovery. Comment the keyword space one last time to show you're committed. Stay curious. Allah Hafiz. The James Webb Space Telescope is only just beginning to reveal what it is capable of. It has already overturned assumptions, but years of operation lie ahead. With every year, it will be probing deeper into the early universe and delivering new surprises. And it won't be alone. The Nancy Grace Roman Space Telescope, NASA's next great observatory, is currently being prepared for launch later this decade. It will conduct surveys on a scale no previous telescope has matched, providing the most precise measurements yet of the large-scale structure of the universe. It will measure the growth of cosmic structure over time with a precision that will either confirm or challenge the standard model's predictions. Ground-based observatories are also being upgraded. The Vera C. Rubin Observatory in Chile will soon begin its legacy survey of space and time. It will photograph the entire visible sky every few nights, discovering millions of supernovae and mapping billions of galaxies in the deepest optical survey ever assembled. Meanwhile, gravitational wave observatories are being upgraded to detect backgrounds from the very early universe, ripples in the fabric of space-time itself. If inflation produced gravitational waves, they should be detectable as a constant hum coming from every direction. This would be the most direct evidence yet for inflation. The Laser Interferometer Space Antenna, or LISA, is a planned space-based observatory that will open entirely new windows onto the cosmos. LISA could detect the gravitational wave background, providing a probe of the Big Bang that is completely independent of the light-based observations we have now. All of this represents the most ambitious scientific effort to understand the origin and evolution of the universe that humanity has ever undertaken. And the pace of discovery is accelerating. Each new generation reveals new features, new anomalies, and new hints of physics beyond the standard model. The picture of the Big Bang is getting richer every year. Thank you for joining me on this incredible series. Like, subscribe, and comment space one last time. Stay curious. Allah Hafiz. So, what is the real truth about the Big Bang that NASA has revealed? It is not a single revelation. It is not one dramatic announcement that overturns everything. It is something more subtle and more profound than that. It is the recognition that the Big Bang, as well as we understand it, is not the whole story. The model is pointing beyond itself. The universe is telling us through its anomalies and tensions that there is more to discover. 13 billion years of history is encoded in the light. 13 billion years of history is encoded in the light surrounding us on all sides, in the background that fills the sky, in the distribution of galaxies, and the subtle correlations that carry the imprint of the very first moments after the Big Bang. And we are only just beginning to learn how to read that code. The truth is, the universe began in a moment of incomprehensible violence. The details of that moment, the singularity, the inflation, the origin of matter, are still not fully understood. The truth is that 95% of the universe is made of stuff we cannot see and do not understand. We are pushing the theory further. The expansion is accelerating. Galaxies formed faster than predicted. These tensions are reasons to look deeper, to remain open to the possibility that the next great revolution in our understanding is just around the corner. The Big Bang happened. The full truth is still being written right now by the instruments NASA and its partners have launched into orbit, by the scientists analyzing the data, and by the generations of researchers who will push the frontier even further. The effort to decode the physics of space-time is one of the greatest intellectual adventures in the history of our species. The universe is older, vaster, and more mysterious than any previous generation could have conceived. It is stranger than we imagined. We are, for the first time, beginning to genuinely read its story from the very first page. Stay curious. Allah Hafiz. Thank you for joining me on this journey. This is Zara Voss, signing off from Threshold Station for the final time. Keyword: space.